So let's prove in this video that every monotonic function is discontinuous at most in a countable number of points. We can write that more properly, saying, okay, we have a monotonic function. It can be increasing or decreasing. Then the set of points of AB at which f is discontinuous is at most countable. Now, monotonic means either increasing or decreasing. So let's say f is monotonically increasing. And let's define E as the set of points where f is discontinuous. I'm being a bit informal here. Now, we saw in the corollary to the previous video we saw a corollary that said that all these continuities of a monotonic function are first kind. Actually, we said that they were not of the second kind. Okay, we said monotonic functions have no discontinuities of the second kind, but because they must be either first or second kind, that's it. Okay, that means they are of the first kind. Here we are talking about, for example, jump discontinuities. Now remember, first kind means that the lateral limits exist. Okay, but they could be different. And they could be different from the value of the function also. Now what we are going to do because f of x minus and f of x plus exist, we can associate, we can take a rational number r that is in between them. Okay, you may object, hey, what happens if there is no space? Is this possible? Well, in this case, we would have a removable discontinuity. Okay, but that is, in this case, the function is basically continuous. So here, what matters is that we have a jump discontinuity. That is, the lateral limits are different, and because they are different, there is a space in between them, and we can take, because the rational numbers are dense, we can take some rational number that is in between them. And actually, we can do this for every discontinuity. So we can call this rational number r of x. Okay. Let's put it here too. So it's a rational number that depends on x. Let me just put it as a subindex. I think it's more clear. There we go. Okay, so given a discontinuity, we can find the rational number associated to it. But now see what happens. So let's say x1, x2 are points of discontinuity. And let's say x1 is less than x2. Okay, they are not the same because otherwise it's silly, okay? Let's say there are two different points. And let's say x1 is less than x2. Then we proved in the previous video that the lateral limit fx1 plus the limit from the right is less or equal than f of x2 minus. And see what happens here. So let's say we have a function here. There we go. And it has two discontinuities. This is x1 and this is x2. So it goes like this and then jumps. Yeah. Well, and then it jumps again and continues. Okay, it's increasing. There we go. Here we see that x1 is less than x2. Okay, but we are also seeing that here f of x1 plus, so the limit here, okay, this is f x1 plus, is less or equal than f of x2 minus, which is this one here. Translated to the axis, we have f of x1 plus, and then f of x2 minus. Now, these two could be equal in only one case, when the function is constant in this part, okay? It cannot happen because f is increasing. It cannot happen that f of x2 minus is smaller. So that's it. But now, see the very interesting thing that happens here. So we have our rational number, r of x1 here, and then we have the other one here, r of x2. So my point with this, with all this, is that r of x1 is different from r of x2. I said I would use, there we go, sub-indices. There we go. And here too. And this actually has, it's what completes the proof. Okay, so what we have proved is that we can establish a one-to-one correspondence between discontinuities and rational numbers. For every discontinuity, we are able to find a rational number. And that means that how many discontinuities can we find? At most, as many as rational numbers. So therefore, at most, a countable number of discontinuities. And that finishes the proof.